record and share my screen. All right, welcome back. And just a reminder that we're Mangata and we're presenting on a low-cost antenna control unit. My name is Jillian. I am also joined by Sebastian, Kyle, Maddie, and Brandon. They're my team members, and we'd like to extend some special thanks to some people at Olin and outside of Olin for all of their help this year. We really appreciate it. And their help has been just amazing in these very difficult hardware times. So just to recap real quick, Mangata is seeking to solve the issue of a lot of underserved regions not having reliable access to the internet, especially during a pandemic in the 21st century. That's a pretty crucial thing to have. And the current solutions for internet at this point are geostationary satellites. They can cover large areas of the Earth, but they can't reach high latitudes as well, hence the underserved regions. Mangata's solution is to have satellites in medium or highly elliptical Earth orbit. They can speed up communication between ground and satellite and also cover those higher latitudes. So just some quick intro to how this all works. Satellites broadcast radio waves called RF, and antennas receive them. And the strength of the signal that you're getting from a satellite depends on where the antenna is pointing to the satellite. So if it's pointing directly at it, you're going to have a great signal. If it's not, you're not going to have a great signal. So with geostationary satellites, you can scan the sky and find your geostationary satellite and stay on it fixed. And that's how broadcast TV and fixed satellite services usually work. Whereas in medium Earth orbit satellites, an antenna control unit, which is what our project was, must be able to move the antenna dish in order to track the satellite at all times. And so we've broken up our presentation into a few different subsystems. We'll first be talking about software, mechanical, and then electrical, and I will let Brandon kick off with the software.
Right, so we'll talk about the software first, just to give you an overview over the general behavior of the antenna control unit. It's designed to be as streamlined as possible. We wanted the average user to be able to set it up, plug it in, and just have it run. So once plugged in, the ACU will start scanning across the entire sky until it detects a satellite beacon. It will track that satellite across the sky until the satellite has dropped below the horizon. Finally, the ACU will move backwards along the path that it was tracking to try and spot another satellite in the same orbit. If it does, it will continue tracking. If it doesn't, it'll go back to scanning until it picks something up. And this will continue until the ACU is unplugged.
So next we can take a quick look at the mechanical design. So we base this design around what we learned from our alpha prototype and our goal of making a low-cost manufacturable product. So the system is essentially a pan tilt mechanism that pans around a fixed ground mounting pole that you can see protruding from the bottom. The antenna mounts on that U-shaped piece that you see at the top with the 4 holes in it. And the internals of the system are housed in a vacuum form plastic shell to protect them from the elements. You can see on the right image, the shell is transparent. So here we can take a quick look at the internals of the system. The main internal body is made out of folded sheet metal, and the mechanisms have been as compacted down as possible. You can better see the ground mounting pole that also acts as the shaft for the pan movement, coming up through the middle and kind of protruding right underneath the horizontal tilt shaft. We can also see that there's ample room at the front for mounting electronics, which Kyle can now tell you a little bit more about.
Okay, so I'm going to go from left to right here on this. Everything starts with the satellite transmitter up in space. It's beaming RF down, and we have an antenna system to catch it. We built ours just for testing purposes. The design of the actual core mechanical and electrical system is antenna agnostic, which means you can just plug in whatever you'd like antenna wise. If you want to do, there's lots of different bands of RF. So you can do a C-band antenna, a KU band antenna, KA band antenna. There's all different types. But at the end of the day, it ends up flowing into our Raspberry Pi, which is the central compute element of our system, via USB. So we are live measuring the amount of signal that we are getting down from space and using that to tune our system. So we're actively tracking to find higher signal strengths. That Raspberry Pi was chosen because it's really convenient, it's off the shelf, and it runs Python code extremely well. So we used it as the basis for all of our software, and all of the software runs the motor controllers, which send electrical signals to the stepper motors, which allows us to track. And those are all powered via a power management board that we custom designed over the course of this last semester in order to fix some of the problems that we were seeing in the first semester. Turns out when you try to have a bunch of motor controllers powered by their own power supplies, in addition to a Raspberry Pi, you have too many plugs to plug into an outlet. And it makes no sense for a consumer to have to plug in that many plugs. And when you have a bunch of cords and spinning movement, tangling happens. So we tried to reduce all of that as much as possible and create a power management board that you just have to plug one AC to DC converter in, and it powers both the motor controllers and thereby the motors and the Raspberry Pi through its general purpose IO pins. So we power the Raspberry Pi, and the Raspberry Pi also can communicate to the motor controllers through those same GPIO pins, general purpose IO pins. And it keeps the system nice and compact with just one plug into the wall. And ideally, as Brandon was talking about, when you plug in the wall, the Raspberry Pi boots up and it immediately starts to track the satellite. Right? I'm going to go back now to the cost comparison because the ACU, the name of our project as originally presented to us was low cost antenna control unit. And so here's some other ACUs. I'll talk a little more in depth about each one. Starlink on the left is the most obvious kind of neck and neck, not competitor because ours isn't on the market yet, but look-alike to ours. And that's because it does the exact same thing. It scans for satellites, it finds them, it keeps continuous tracking of them, and it costs $1,500 to make. So SpaceX is currently selling them at $500 and just taking a bath on the rest of it. This is why it is very difficult to create ACUs that are as cheap as they can be. The next antenna is a DirecTV King antenna that you would put on your RV, and it's great, it moves, but it's designed to move after you've stopped and then point at a geostationary antenna and just stay there. It doesn't have the software capabilities of being able to track a moving satellite. The extreme end of that is the marine internet antenna, which you'd put on a boat that's constantly rocking back and forth. So it can cancel out that movement magically and stare at a satellite. So you have internet on the boat, and that costs $30,000. So these devices all either cost nothing or close to nothing, $400 for your DirecTV antenna, or they cost a lot because they have to move. And so we're trying to cut down the cost here, and we think $750 is a really good start. The caveat that I've been telling people on this is that does not include the satellite, the dish cost. As I said, our device is antenna agnostic, which means that antenna cost is going to end up being a large portion of that. However, we think $750 is a great starting point. We spent a semester trying to optimize the cost, and we think if you spent a lot more dedicated time on it, you could just drive the cost down even further, which leaves more room for the satellite dish to not be as big of an influence in the price. Okay, speaking of next steps, we think the major next step is going to be manufacturability and cost optimization. So actually building the beta prototype as it's designed, finding out what's wrong with it, fixing it, and driving that cost down even further, both in terms of assembly cost, manufacturing cost, quoting cost, all of that, really trying to drive the price down. An upgrade to the service antenna. We chose ours to be a KU band, which is great if you're pointing at geostationary satellites, but less good if you're trying to point at something in lower orbit than that. Eventually, the service will be in the Ka band, and so we're looking for a custom, probably antenna solution that will eventually be mounted onto this for full time. And then further software development. We know the bugs that exist in this. We've spelled it out in our final report to the future teams that pick this up. But it would be really great to have somebody sit out there, run it for hours, days, weeks, and just see what trips it up. The concept for this thing is that it sits out on your lawn or on your roof or wherever you want to have it, and it works forever. It shouldn't ever get tripped up by itself. How close we are to that? Questionable at the moment. However, the next team is definitely going to want to push that as far as the envelope can go. Okay, that's a lot of talking. Let's do some Q&A. If anybody has any questions.
If you don't, I'll just start asking myself questions. So.
Well, we wouldn't want that.
How much do antenna dishes cost? Like in comparison to the $750?
That's the part that we weren't able to figure out very well. A lot of times when you're in the Ka region, these antennas are custom designed in-house, and they used phased array is what they're called. So they're not just parabolic dishes. So they're very fancy antenna that cost a non-zero amount that could be very expensive, which is why it's super important that we drive the cost down on the mechanical part, because if that ends up being $1,000, if our thing cost $100, suddenly, we've at least undercut $1,500. So that's a win. But yeah, antennas are expensive. Oh, I got a question in chat. Power constraints. You need to keep the motor constantly powered so the dish doesn't tip over. So there's stepper motors. And maybe, Jill, you could talk a little bit more about power requirements. I don't know how close we were to actually maxing out just a single connection 24-volt DC. I don't think we were very close. The steppers don't need constant power in order to keep them from dropping, which was probably the nicest thing. They're not direct drive DC motors.
Yes, I think it was a 2 amp peak on the steppers, and it was not very high in terms of. I know at least for the Alpha, we were able to run it off of one power supply for both motors. So.
Yes, it is not that much power in order to run. Is there an issue with latency with tracking the satellite and positioning the antenna? Trying to parse the question of like where there would be latency. There's definitely like latency that happens, and this is why you use a phased array. Is with a phased array, technically you can point at 2 satellites at the same time, which makes handover really easy, and so you don't have like loss of signal while your antenna rotates in order to find the next satellite. That in our current design does exist. I believe Mangata had wanted to set up a series of 2 of these things next to each other so that one was always at least pointed at a satellite while the next one tracks over. Another good reason to spend a bunch of money and design your own custom phased arrays so you don't have to spend all that money on a second ACU. That's the latency that I've seen a lot of times.
In terms of calculation and motor movement latency, like time to receive the signal, calculate the signal strength and convert that into a set of motor commands and move those, we did not find it to be a problem, especially because our motors are spec'd for a significantly higher maximum movement speed than what we would be expecting for a mid or higher mid-Earth orbit or a highly elliptical orbit.
Mahmoud, si je unmute, vous n'avez pas de micro là? Non.
Vous voulez poser une question?
Oui, mais il n'est pas set-up là.
Non.
Anything else?
Yes, I think we just got our 2-minute warning. So if anyone has any last questions before we wrap up, we'll we'd be happy to answer.
It was pretty awesome.
Thanks.
If
Good
no one has any
time.
questions, I just wanted to say thank you all for coming. It really means a lot, and we're happy to have you here. Also, now is the time if you would like to go check out other scope presentations that we encourage you to do so. There's a lot of cool projects happening, and we don't want to hog all of your time.
Yeah, absolutely.
Thank you for coming. We'll switch over to the next group.
Oh wait, Ian,
Yeah.
before you leave, this is the part where I subtly talk about rocketry. I heard the new boards came in. Are they being assembled?
They're being assembled later today.
And if they work, we're going to use them. We're going to use
Yeah.
more of them, right?
Yeah.
Oh, that's awesome. Okay, cool. I was just curious about what the status was on that.
Kyle, I don't think you and rocketry and subtle all belong in the same sentence.
No, they don't. It's really just like a bat with spikes on it. It's not subtle at all.
It's not, but that is a-okay.
About as
Jill, it
get
might
paid
be
by a
time.
bunch of college students.